Okay guys, let's talk about some more about operational amplifiers, about measurement amplifiers as we did before in the last two parts. Today I'm going to talk about some specific electrical circuits often used within or with operational amplifiers. The first circuit I want to talk about is the impedance converter, which is a very simple one and at the same time a very important one. So we have that operational amplifier, we have some input voltage UE over here connected to the ground, and we have some output voltage over here also connected to the ground, and we do a feedback loop directly. So we couple back, we recouple the whole output to the input. What do we get? Thinking of the last part, we build up a mesh like this. We know we are recoupled. We have a feedback loop. We know that that voltage over here has to be zero. And so we know UE plus 0 minus UA, that's the whole mesh, equals to 0. That means UA equals UE. That means the amplification factor of the whole system is 1. We would expect that. Remember of the part where we did the general, recoupling the general feedback loop, which told us it's 1 over kg. Now kg is 1, so we get an amplification of 1. The result is quite expected. But now the question arises, why the heck would I do such things and use an operational amplifier having no amplification at all? The answer is quite easy. We know that that operational amplifier has a very high input resistance. And now, doing some electrical calculations, we won't go into details about, but doing the feedback loop over here, the input resistance of the whole system, so the resistance which is seen from the inputs where UE is connected to, even rises more by recoupling, by doing that feedback loop. Meaning, that resistance over here, that input resistance of the whole system rises even more, goes up to infinity. Talking about numbers, assuming we have an input resistance of 10 mega ohms, the operational amplifier, that's a typical value. That whole thing gets an even higher input resistance by a factor of the amplification factor of the operational amplifier. So assuming we have 10 to the 6 as the amplification factor of the operational amplifier, we get 10 mega ohms times 10 to the 6 input resistance over here. That's awesome. Think about photodiodes, which have resistances between 1 mega ohm and nearly 0 ohm. We now have a system we can just connect to such a photodiode or a photoresistor, and taking that voltage, not having to deal with the high resistance of the photoresistor when it's dark, because that thing has an even more high input resistance. Great. On the other side, the output resistance even falls to smaller values, goes to 0 nearly. Again, the same factor, kind of K-line, kind of the operational amplification of the operational amplifier, so we get a really small output resistance, which makes it very easy to measure that voltage UA exactly without any systematic errors. So that impedance converter converts a very high impedance over here, for example, of a photoresistor, to a very low impedance at its output. Great. Impedance means resistance. That's the first thing, the first circuit I wanted to talk about. The next circuit I want to talk about is the inverter somehow, because it's the other way of doing feedback loops with operational amplifiers. So looking at it, note that minus now is at the top side. We get some nearly identical setup. Over here there's the ground. Connected to the ground is the plus input. And now the output again, UA, is partly recoupled through a resistor R2 back to the input, whereas here is another resistor R1. What the thing does, it's called inverter, it inverts the voltage UE, meaning it applies a minus to it. How do we get to that point? The main idea is that no current can flow in here. So we have currents over here, I2, and currents over here, I1, which all head up into that knot over here. And now we know that input current I2 plus I1 has to add up to 0. That means we get an amplification of the whole system, okay, so I2 equals minus I1, I1, and so we get an amplification of UA to UE, which now can be denoted as UE is the voltage which falls along R1, so it's I1 over R1, that's UE. Now UA is the voltage which falls during that mesh along R2. Now I1 is minus I2, so we just simply plug in the minus over here, I1, and get an R2 over here. And so crossing that out we get minus R2 over R1. Nice, that's the minus. That's the reason for that inverter. So we invert the input voltage. And moreover, we have some way to define an amplification by the ratio of R2 to R1. Having said so, normally you would not use that electrical circuit for amplification because the whole current I2 has to come from your operational amplifier, from your external voltage source. And normally those operational amplifiers aren't able to generate high currents. So, doing so, we are somewhat restricted with the amplification factor by the current which we have to deliver at the output of our operational amplifier. Having said so, we denote one more thing, looking at R2. No matter how large R2 is, the current flowing through R2 has to be the same current as I1. So now let's assume we define the current I1 by choosing R1. By that we can define a current. Applying UE, choosing R1, we can define a current I1. That's Ohm's law. Now that current has to flow along over R2, no matter how large R2 is. And now what we get, thinking about that, is a current source. Because that source over here delivers always enough current it delivers always the current which is needed to compensate the current I1, no matter how large that resistance R2 is. Meaning, you don't have to care about R2. You can choose it arbitrary, but the current flowing along it will be I1 over here. That's a current source which delivers a certain current no matter which resistance is applied to it. Okay, but that's something which just gives us a glimpse of how current sources can or could work. Let's talk about some other circuits which are somewhat interesting. One of them being the substraction amplifier, which indeed needs some further calculations I won't derive over here. There's everything denoted in the script, and it's not very complex, but it extends somewhat the electrical circuits beforehand and needs to apply both ideas of having zero differential voltage and a zero current into the operational amplifier. But let's just look at the circuit so we see how it looks. So we have somewhat an identical situation for that substraction amplifier as for the inverter, by having the coupling done like for the inverter at all. But now that plus is not directly coupled to the ground, but split up into two parts. Note RG, R and R, so those are the same resistances over here, whereas a second voltage UE2 is connected over here, also relative to the ground, and now the rest is connected to the ground, and we get our output voltage over here. Okay. What does that thing do? By adding that divider over here, that minus which is produced over here results in that subtraction. Just to frankly describe how that circuit works. In the end, what we get as a result is that UA, let's write it in red as beforehand, that UA is nothing more than RG over R minus RG over R times UE1 minus UE2. So you see we have a subtraction over here. Okay, as I said, I won't go into detail about that calculation. You can see that in the script. It's out there anywhere, and it's not that complicated. It's just using those two main rules we've learned beforehand. But what we see is we can subtract two voltages. Now, one could ask why to subtract two voltages. We have some PCs, we have some awesome digital stuff which allows us to do subtraction very strictly, very correctly, without having such an analog device or whatsoever. And the idea why a subtraction amplification is important is not the subtraction of the voltages itself, but that you are able to take two potentials relative to the earth and subtract them from each other. One simple case you need to use such an electrical circuit are those measurement bridges. Think of those measurement bridges over here. We already did in the chapter for resistors. And we want to measure that voltage difference within here. So for that case, we would connect the two poles to the operational amplifier system of a substraction amplifier. Why not using some other amplifier? Remember, all those input voltages were relative to the ground. And now connecting that side of our bridge would ground the bridge within that place. So we would change our electrical circuit of our measurement bridge drastically. We can't do that. We just cannot introduce a ground within any existing electrical circuit. But when you use that substraction amplifier, we can just take that potential, that voltage relative to the ground, that voltage relative to the ground, and subtract them from each other. So we get the differential voltage between those two connectors. So that's the reason for subtraction amplifiers. Often subtraction amplifiers are combined with impedance converters or electrometer amplifiers, which allow then to amplify those voltages and then to subtract them, all together built into a difference amplifier, an instrumental amplifier. There's some stuff about that things in the training exercises you have access to via the artificial intelligence. And that's mainly the whole stuff, the whole range of circuits of electrical amplifiers used out there. There are a lot of other amplification circuits for adding voltages and so on and so on. And at some point it's sensible to use them. But on the other hand, as soon as it gets into real calculating something, you would do that digitally. You would not rely on an amplification circuit like this. So now let's talk about the last thing, which can be very interesting, which is the comparator, which is the simplest one actually. It's just the whole thing relative to the ground, whereas we have a reference voltage over here, an input voltage over here, and an output voltage over here. So we have no feedback loop. Calculating that stuff is hard, even impossible, but we don't have to calculate that stuff. Why? Because we know everything about it. Think about that output voltage being here and that input voltage being on that axis, and now denote the reference voltage over here at that place. What will happen is the following. Whenever we are smaller than the reference voltage, we have a negative input over here, and that will be amplified as hell by that factor over here. 10 to the 6 or nearly infinity, or even infinity for our ideal operational amplifier. So what we get is a real high voltage over here. How large is it? It's the maximum voltage our external source of our operational amplifier can provide for the real case, for the realistic case. There's no voltage that could be produced at the output more than the maximum input voltages. So it's U+. Then coming near to that reference, we very abruptly switch to the other side over here, to the other voltage. Let's exchange the plus and minus. That doesn't matter at all, but just to see what happens, it means we get the maximum output voltage we can have. As long as we are smaller than the reference voltage, then we get the maximum output voltage on the other range, as long as we are bigger than the reference voltage. What is that used for? It's digitizing signals. That thing allows you to compare the reference voltage to the input voltage. That's what it's all about. You know when you're smaller than the reference voltage, you know when you're bigger, and you get a zero one signal, a digital signal at the output of the comparator. That's why it's called comparator, because you can compare two voltages. And that allows you indeed, when talking about analog digital conversion, to get a glimpse, an idea of how analog digital converters work. They normally just compare unknown input voltages UE to known voltages U reference over here. And by that are able to give you a digital equivalent of the voltage, the unknown voltage applied to the system. But we will talk about that stuff more in the chapter about digital technologies. So long, have fun, see you.